Hi, my name is Venkat. I am here in affiliation with the University of Virginia to present Energy Harvesting Systems Need an Operating System too. So the direction that embedded devices are going with the variety of CPS and IoT applications, we're calling on them to be more and more sophisticated. We want responsiveness, sometimes close to real time. We want security. We want them to be easily programmable, and we also want them to be in operation for very long periods of time. The sophistication and complexity that we want from these devices is enabled by having good software support. So there's two key aspects to this. The first is robustness, so having a bug in the code shouldn't break the entire system. But we also want scalability so that every time a new hardware platform or hardware feature comes out, we're not writing monolithic C programs, and rather we're having an operating system with principled abstractions that we can reuse. And that way we can embrace new technology faster. So embedded operating systems, though, have to keep up with the sophistication that we want. At the same time, device hardware is becoming more constrained. We specifically are talking about lower energy and energy harvesting devices, which kind of paves the way to intermittently powered devices. And the operating system has to mediate that, the increase in sophistication, while also masking the changes in the hardware. And so we're gonna explore using an embedded operating system in the context of intermittent computing. In this work, we use the Talk operating system. Talk is a secure embedded operating system with the kernel written in Rust, which is memory and type safe. So some of the reasons that we went with Talk. So Talk basically has this process abstraction where the processes are sandboxed. So if one process has a fault, it won't cause a problem for the entire system. But also, if we think about the longevity of these devices, it becomes clear that there's a real possibility that we'll need to update them over time. And so keeping the footprint of application updates smaller, because if you have basically all of the application code compiled in with the software system, you get a much bigger binary. Keeping the size of that down can be really useful. So quickly go over the agenda for the rest of the talk. We're going to go over some background and motivation for this work. We'll talk about our vision for energy harvesting software, and then we're going to go into actually the extension that we made to Talk, and then the evaluation of that, the limitations and future directions of this work, and then we'll conclude. So basically writing applications on intermittently powered devices is very difficult because every time the device turns off, the volatile memory resets, and then you kind of get stuck back at square one. So basically, you have to find a way to make forward progress and optimize your use of the harvested energy. And so there are basically two ways in prior work that this has been done. The first is checkpointing. So in this example, you might have a point in your program where you check the voltage, see how much energy you have left, and then if the device may die soon, you'll store a bunch of process state in some non-volatile storage. And then when the device comes back online, you read your state back in, and then resume execution from the point that you left off. This can be costly because you can often have lots of state to write, plus doing the energy level checks. And then the other way to make forward progress in prior work is using a task-based approach. So basically here you break a monolithic program into smaller tasks that are energy atomic, so they have to complete in a power cycle. And this sort of puts effort on the developer to break the programs down. However, you end up with less state that you need to store, because basically you enforce the order of the tasks with a task graph, and then you just need to save where you are in the graph and then the information that's being passed between the nodes. So one of the motivations for our work can be seen when we look at the body of software systems for intermittent computing. A lot of the systems are kind of custom made for a narrow selection of hardware. So that's usually like a TI MSP type platform, and that includes the WISP, which uses a TI MSP for 30 MCU. That also includes the energy sources. Usually these systems are using RF. And so there's a bit of stifling in the development of these energy harvesting devices and the applications for them, because we're not using and exploring kind of viable energy sources and hardware. And intermittent devices, they're becoming general purpose. Looking at the hardware in the last couple of years that's come out, like Flickr and Capybara, they're offering a lot more flexibility. For example, Flickr has this modular design that allows you to swap out peripherals to not just constrain the research to using RF. On the software side, we look at the approaches to making forward progress. And if we compare a checkpointing system from 9 years ago to today, the complexity and the flexibility has increased a lot. Before it was statically placing trigger points, and now you have a bunch of different ways to place the points depending on the use case, and sort of other features to combat issues with prior system, like time sensitivity and memory consistency. And our vision for the future of energy harvesting software is that it should be flexible and it should be future-proof. On the side of flexibility, we should have reusable applications, be able to use different languages and not just C, maybe Rust or even Python. We can use checkpointing and task-based approaches depending on when they're appropriate, because they both have use cases that they serve differently. And then in terms of updates and future-proofing, if we want devices that will be in operations for decades and decades, we need to look at the possibility that we're going to have to update them, whether that's security updates, whether that's updates to an application or algorithm. So an example here is something called it was derived from something called Energy Cam. Basically, Energy Cam is a continuously powered device that takes a photo of a meter or a gauge and then digitizes it and transmits it. And so basically, you can retrofit old meters and gauges instead of kind of ripping them out and putting in smart meters and gauges. So the idea here is that you take the picture, do some image processing, and then transmit. And so there seems to be kind of a use case to make this energy harvesting, because where this was tested out, I think in Munich airport alone had thousands and thousands of gauges and meters. And so if you scale this up to other places that you would want it, it quickly becomes clear it could be an energy harvesting or batteryless device. So in a case like this, you can imagine wanting to update it over time, but you could see maybe like the photo taking and the transmission code being the same, but maybe you want to update the image processing. Then you can just update that portion of the code. You can also imagine that a device might want to change functionality, maybe over long periods of time, or even what it runs between the daytime and the nighttime. So you could have, for example, a bunch of applications stored in Flash, and maybe change which applications are actually running. And another thing is having the operating system can be useful to do updates, because it can do some validation and security checks. Now we're going to talk about how we actually extended TOC for task-based intermittency. We chose task-based because basically TOC has these processes that we felt mapped well to tasks. So basically, as we saw before, this is just kind of a simple task graph. And this is how they map to processes that use this called interface to interact with the kernel. And then this last diagram is basically how the data is passed between processes. So a process writes its output to its own memory space, and then the processes that are dependent on it will have a pointer to that output. So I'll go through a list of the features that we added so that TOC could make progress in face of power failures. So the first is having the graphical representation of tasks that can be passed to the kernel. The second is basically using the existing TOC capsules and drivers to save enough state to non-volatile memory so that we can actually resume and make progress once the device starts up again. We augmented the scheduler so that we could parse through the task graph and actually enforce the order. We introduced a new inter-process communication mechanism. TOC already had one, but it didn't really lend itself well to a task-based approach that we wanted to use, because basically the processes have to coordinate with each other, and so we used a new inter-process communication mechanism. And then we also augmented the syscall interface. There wasn't really a need before, basically, for a process to signal to TOC that it had ended, but basically to be able to enforce the order of the tasks, we had to be able to do this, so we introduced an exit syscall. Okay, so let's talk about the experimental setup. So we chose to use the MX hardware platform. It does have a lot more RAM and flash storage than some of the related work systems, but we chose the MX because TOC is quite stable on it, and we wanted to start testing the feasibility of this extension without changing too many parameters. We created a simple lighting control app that basically took a sample and then did some computation and then transmitted that value. And then we calculated some time and memory overheads. We also commented on the developer overhead. We simulated intermittency on the system by running a task and then restarting the device. We also had an additional implementation just to explore this idea of changing a node's functionality after deployment. So we basically had two different task graphs that, depending on a GPIO signal, the kernel would use a specific task graph and then only pull those applications into memory to run. So it kind of explored this idea of, okay, sometimes it would sense and print the temperature, and then sometimes it would sense and print the light. So looking at the overhead results, in terms of the time overhead, the functionality that was added, so if we look at basically the startup cost, because that's what is consistently happening every time you restart, the reading state from Flash and getting ready processes and scheduling basically only added about 6% to the startup time. And then The largest cost was actually the peripheral initialization. And so one way to mitigate this would basically be to add a feature that only initializes the peripherals that are being used by the applications that are being run. And then additionally, there was a large cost associated with writing to Flash. And realistically, 2 ways to mitigate this are either to use FRAM or to really just not save state as aggressively. In terms of the memory overhead, this augmentation poses significant change to the functionality of talk, and that's reflected in the memory usage. There was a lot of care taken around copying and things that I think could be optimized in the like getting ready processes and scheduling stuff. On the app side, basically the apps all like had printf stacks, and they all have their own instance of a library, and so they are quite large compared to prior work systems. Because each task maps to its own process, it creates a fair amount of overhead. So in terms of developer overhead, there's potentially like one less task to learn, or one less construct to learn, because processes map to tasks, but otherwise it's pretty comparable. And the other thing is that there's a lack of universal IDs that the kernel and the developer understands. Basically, there's a talk utility that assigns an ID, so that can be a little bit cumbersome. But I think there are places moving forward to optimize, and this is kind of an interesting result. So on to limitations and kind of where we're going, where we can go with this. I'll highlight a couple of these. So basically a limitation is that talk loads all the processes from a task graph, or all the tasks that are in a task graph into memory. And so it kind of limits the number of nodes that you can have in a task graph. We started work on only kind of loading in the necessary processes, but that is not completely built out yet. And then I mentioned the universal ID. And then checkpointing is a feature that we want to look at. Maybe talk will lend itself better to checkpointing, or lend itself well to checkpointing, because the task-based approach kind of has all this process overhead. Checkpointing might be an interesting way to go. So in conclusion, we proposed our vision for the direction of intermittent computing and the software systems. We extended talk for intermittent computing and for making progress through power failures. We assessed the overhead of that, and we also assessed the constraints of talk to being adapted for this type of workload. And I think the takeaway here is basically that there are going to be systems that we want to be single purpose and that are constrained to the point where running an operating system is not feasible. However, looking at where we want to go, moving away from kind of having application specific and hardware or software systems that are custom to the hardware will ultimately make it easier to develop and deploy the number of these devices that we want to. Thank you very much.